Good afternoon, everyone. My name is Ryan Bobryk, and I'm here with Corvid HPC. And we're here in our partners Ace Computers booth here at SC25. And today, I'm going to be presenting on how HPC as a service can close the gap between your physical on-prem HPC infrastructure and your current workload demand. So if you're managing HPC assets, whether that's currently on-prem, in a colo, in a coat closet like we used to do it at Corvid back in the day, or potentially in the cloud today, you're probably very well versed that as we add hardware, we can only add it based on delivery schedule, timeline, and what can really pay for it. So we can run into where we never have the actual amount of hardware. So then a little tough to see, but here in gray, we have that kind of large delta where there's always some amount of work that's not getting done. Very common problem. And what we're here is really to talk about how our solution for bare metal HPC as a service can fit that need. So what's really driving this being an accelerated pace, here today in 2025 as we move into 2026 comparative to 5 or 10 years ago? Well, two key trends that are really kind of going big right now. Simulation, scientific computing, and AI workloads are not, they're not slowing down at all. If anything, people are doing more simulation than ever, more scientific computing than ever, and more AI than ever. And the second part is the timelines for completing the singular runs that, let's say the timeline used to be a week. Now, we're compressing that down even quicker. So even though we're delivering better performance, now the engineers who are relying on those answers are getting accustomed to that even tighter product development schedule, and now it's becoming a hard set requirement. So everything keeps shrinking from a timeline perspective. We all know that fixed capacity, especially when used at 75% plus allocations, it's going to be the most economical solution. If I buy a large scale system, let's say for $1 million, if I get 80% plus utilization, that's going to pay for itself in no time. However, do you really have workloads where you can buy at scale and use it 80% of the time and make sure you have jobs queued up 24/7, 365? So there's certainly some limitations there. So, really the main, that's the problem, but the main solution recently has been customers really trying to go to the cloud for fitting that need. But we've seen that there's quite a bit of barriers. Some people straight up are not successful at all. Some people are moderately successful. And then some people who would say they're very successful, but even those customers who would self-report that they're very successful bursting into the cloud for CAE, scientific computing, and AI workloads that have come from on-prem HPC are still running into a number of issues. So we recently had a customer who had 700 plus Fun3D, which is a computational fluid dynamics code from NASA. They run these 700 cases to properly characterize the performance of their aircraft through a variety of altitude, speeds, and other thermal conditions. And so you would think, hey, this seems like a slam dunk. I need instant capacity, ready on demand, and I need it to run fast. Well, what we found was that customer, comparative to our bare metal HPC as a service, was having a pretty huge core-for-core penalty degradation. We saw 30%. On the following slide, we're going to walk through that in a little more detail. Also, workflow migration. If I'm coming from a standard on-prem HPC deployment and now I have to go to the cloud, there is engineering effort, workflow mitigation, and things that I need to do to work around some of the complexities of working in the cloud. The software stack that these hyperscalers have come up with, it's really for them to manage them selling you their compute, not the other way around. It's really not for the customer to be successful. It's the other way around. So that way they can deliver it at scale. Genius business, but maybe not good for CAE workloads. And then also when you have such large needs, we're talking 10 to 20 to maybe even 30,000 cores needed here to run these types of cases in such a condensed timeline. Typically, unless you're already at an 8-figure commitment with these companies, you're not able to get access to 20,000 nodes on demand unless that was your previous agreement. So there still is some type of mechanism for your compute reservation that does take time to set up. And then lastly, security. Most of our customers are operating with some level of security. This customer in particular was running, they're a defense industrial based contractor, which means they need to adhere to the new CMMC requirements. Now, all of the infrastructure they're running on the hyperscaler is all FedRAMP compliant. But unfortunately, when teams who need to move really quick and they're run by engineers, those engineers not always are going to set up everything from scratch in a manner that is fully compliant. And then I would bet even if they are setting up in a fully compliant manner, they're probably not documenting it to a T to where they get their CMMC assessment and that assessor walks through that environment, probably not documenting at the level that's going to make that assessor happy. Therefore, they would technically be out of compliance or fail their assessment. Why would we recommend our solution for this? We are 29% faster, 4th gen to 4th gen AMD. Even when we compare 3rd gen bare metal to 4th gen hyperscaler, we're still 11% faster on average. This is with NASA Fun3D specifically, but we've reproduced these results with a number of different CFD codes, common codes like ANSYS Fluent, Siemens PLM, SimCenter, Star CCM, and other DoD and industry codes as well. So we looked at the table. I'm not going to narrate the full thing, but it's clear. We ran 4 very different use cases at the customer that each represent a significant amount of their workloads to kind of create a homogeneous average numbers that we can then scale and put a direct number onto the savings and speed. And what we see is anywhere from a 25 to a 32% speed up on the Genoa to Genoa comparison. And then same thing, anywhere from a 7 to almost 14.5% with Genoa to bare metal Milan. So what this means to this customer is not only decrease in time to market, but also roughly a 30% savings in cost. So then you think about it and you go, well, you know, if you're bare metal as a service, can you really keep up with a workload that big? That would be, you know, when we call customers, that's their main concern. Do you have the capacity to meet my needs? So we actually ran through this with this customer and did this as an exercise where they ran a large amount of this database. And basically what we found was we were able to facilitate the 700 cases in less wall days than they were on their current reservation of their current cloud. In order to increase that reservation, they would actually have to spend more money to do that. And then when we look at the out-the-door costs, we're estimating core for core about $420,000 with our hyperscaler provider and only $200,000 for us in less days to market. So, you know, this data really speaks to everyone in their organization. The engineers are thrilled because they have an HPC bare metal environment that really speaks and resonates to the workflows they want to use. They're getting their answers faster. And then everyone up the food chain all the way up to the C-suite is thrilled that they're saving roughly 50% core for core. You know, so what should true HPC as a service look like? Well, as we talked about earlier, cloud's been filling the void. It's been doing, you know, the best it can for these types of scientific computing, simulation, and other types of workflows that just work better on a bare metal system. So, you know, really the 4 pillars are going to be tried and true HPC technology. You know, all the software is designed to run in a bare metal environment. So we're going to match you there. We've got a dedicated network, web server, and file system ready to go out of the box. So that way our standard end users do not have to work with HPC or network administration tasks. On-demand capacity and performance with no penalties. And lastly, a consumption and pricing model that just makes sense. Really easy to predict cost, really easy to sit down at the beginning of a workflow and say, hey, how many cores, how many hours am I going to consume, and come up with a rough cost. Whereas on the other side of the fence, our customers tell us they really struggle to predict what's the actual storage cost, what's the actual network transfer fee going to be, and then how much data do they need to put in their calculator for egress. So when it comes down to it, they're able to easily predict their core hour costs in both environments, but the total cost of ownership for certain workloads can certainly grow in the traditional cloud perspective because of all those add-on fees. So how could we get to the scale where we're able to deliver this, you know, at the level where we have enough cores to really work with these larger workloads? Really, it all comes down to our parent company, Corvid Technologies. So starting in 2004, you know, David left Dahlgren to start Corvid Technologies, and you know, HPC has been at the backbone of that. And at the backbone of us buying HPC has really been the relationship with Ace Computers. We've now worked up to the point where in 2019 we built our own data center. In 2021, we incorporated and turned Corvid HPC into an external sales environment. And then, you know, what does that mean for today for both the growth of Corvid Technologies as Corvid HPC's largest customer today, and then our external customers, you know, really as we've helped them grow to 550 employees, 10 plus offices, you know, really supporting the DoD community in key areas like missile lethality, weapons effectiveness, and hypersonics. We're a managed and pre-configured solution, so that means we offer these software stacks ready to go out of the box for our ideal customer profile. We're always adding new ones to this. It's something that just as we go, we're continually adding to support a larger and growing customer base. And then one of the things that makes us unique is the ability for our customer, no matter how technically savvy they are, to meet them where they are. So if you're a tried and true HPC delivering, Linux today to your customer base, we can support everyone just running their jobs through Slurm Submit and CLI. Let's say that they're running a tool that has a Linux GUI. We have a lot of customers using ANSYS and Star CCM directly in the GUI. So we have customers who have only ever run on a Windows platform, not really comfortable running anything in a command line interface. We've got a great solution for them. And then for tools that don't really have any of that Linux GUI capability, we've built these Python submission apps to make it easier to run HPC workloads right out of the box. All they have to do is comment what they need, what they know about their job, pick the amount of resources, and hit go. And to kind of wrap and talk about the state of the industry for HPC. So we see three types of providers here on the cloud side. You're going to have your large-scale cloud or your hyperscalers. You'll have your digital platform resellers. So those are companies who are basically creating a middleware layer to help people who are not as skilled run in the hyperscalers. And then you're going to have the software OEM cloud. So that's like a company like ANSYS having like an ANSYS cloud or Siemens PLM having SimCenter X. Both of those companies we have technology or cloud hosting partnerships with. And then we have our solution on the right, which is really delivered around remote HPC, designed from scratch for real-world production engineering workloads, bare metal performance. We're 100% US-based. Any ITAR, export compliance, CUI type workloads you can run, we can run it out of the box. And we're built and supported by simulation users. Thank you very much for joining me here at Supercompute 25.